Look at this. This is page 146.
146.
Yep, page 146.
Oh my gosh, there's so many.
Let me show you this first, and then I'll show you what I highlighted. If you write the first derivative as y, you write the second, or y prime, you write the second derivative as y double prime, and the third derivative as y triple prime. If you write the first derivative as f prime of x, you write the second derivative as f double prime of x, and so on. This gets a little bit crazy. If you write the first derivative as dy over dx, then you write the second derivative as d2y over dx2.
Why?
I don't even want to go there. All right, I never write a second derivative. I never write a second derivative that way. I just wanted to say that I had shown you those ways of writing the derivative. You're never going to see me write any of those. I'm going to stick with y double prime or f double prime. All right, the other thing I wanted to show you is what I just said. Just as you obtain the velocity function by differentiating a position function, if you take the derivative of the velocity function, you get the acceleration function. So if s of t is the position function, s prime of t is the velocity function, and, whoops, sorry, crap. And the derivative of the velocity function, which is the second derivative of the position function, is the acceleration function. The acceleration function is an example of a higher order derivative. So we're going to do one problem from 95 to 102. You have to do those in your homework. They say find the second derivative. I'm just thankful I don't have to find the third and fourth derivative. Look at number 96. I'm not going to write it down, but that one won't be bad because it doesn't use the product rule or the quotient rule. If I don't have to use the product rule and the quotient rule, I'll differentiate all day long. Number 98, can you write it so that you don't have to use the product rule or the quotient rule? Yes, you can divide x into each term. Number 100, remind me of the derivative of secant.
Secant tangent.
Derivative of secant is secant tangent. Y'all, it's okay if you don't have that in your head yet. I just told you 2 days ago, but by the test you have to have it. Derivative of tangent is secant squared. The derivative of secant is secant tangent. And then I'd say 102 is what?
What about the other one? So like sine, cosine, cosecant.
They're all in the inside cover of your book, which you cannot use on the test. All right, 102. It's the hardest, so let's do it. I know it's going to be yucky because I'm going to have to use the product rule, and that's going to give me an ugly answer, and then I'm going to have to differentiate that ugly answer again. So I always want to do the hardest problem as an example. That way I can say I tried to prepare you well. 102.
Somewhere, like on my stomach. What are you doing? Nothing.
Every time I start to say by the product rule, I want to say by the power invested in me. Maybe I get my power from the product rule. By the power invested in me, by the product rule, h prime of t, you've got to recognize that as a product. If you need a dot to help you see that, put it there. If you don't put it there. The first times, what's the derivative of the second? Cosine t plus the second times the derivative of the first would be e to the t. Have I completed the product rule?
You could
No, you can simplify it.
Yeah, I could do some algebra maybe, but I finished the product rule. Here's the first derivative of the second plus second derivative of the first. Now it's up to me whether to simplify that before I differentiate or wait to simplify at the end. I'm telling you, it's not going to be pretty either way. It's not going to be terrible, but it's not going to be cute. I think I would like to go ahead and factor out the e to the t and leave the cosine t plus sine t in parentheses. But when I find the second derivative, it's going to take the product rule again, because that's what that is. That's a product. Make sure you write h double prime of t. You need to label what it is that you're doing.
So now we're taking the second derivative of it?
Yes, sir.
Alright.
All right. First factor is e to the t. What's the derivative of the second factor?
Sine t minus cosine t.
Negative sine t plus cosine t.
Did you just write that as cosine t?
I would personally, if I wasn't giving notes, that's exactly what I'd do. Negative sine t plus cosine t. And am I finished? No, but it's hard. I mean, calculus just goes on and on and on, and you have to think really hard about whether or not you're through. I'm not. All I've done is the first times the derivative of the second. I have not done the second times the derivative of the first. There's the second times the derivative of the first. Then what? That will definitely clean up significantly.
You'd have to change your sign though and make it
Change my sign.
because if you're taking
Yes, it's
derivative first time to second, that's e to the t times
Cosine t plus sine t.
Yeah.
Okay, let me suggest a different way of thinking about it, and if your way leads to the right answer, that's fine. But I was thinking, now wait, why are you saying I have to change my sign? That cosine is,
second.
But no,
Next one.
Right
the
there.
sign of
Next
the sign.
Awesome.
It's plus.
oh, I'm sorry. Okay, that wasn't just a different way of thinking of it, that was the wrong way of thinking of it. I'm just as hard on myself as I am on you. That was just supposed to be the second factor as is. I made a typo copying it. I wasn't doing a calculus thing. That was a typo. All right. That takes care of one thing now that I cannot do because these aren't the same. But what I would do is factor out an e to the t. And what would that leave you inside a great big parentheses?
E to the t squared.
Yeah. Plus cosine plus sine.
Yeah. If you can skip a step, feel free to do so. For those folks who don't like to skip steps, here's what you need to write down. And what does that inside parentheses clean up to be? Just 2 cosine t. You would normally write the 2 as the coefficient, and then the cosine t.
If we on the test, if we left the 2 there.
Squished in the middle like the filling of an Oreo. I am so happy you have done so much work here. If your 2 is stuck in the middle by the commutative property of real numbers, it is right. It's right. It's goofy looking, but it's right.
So why exactly do we get the double derivative?
Because that's what the directions said. I am going to come to Harriman and punch you. The directions said find the second derivative.
Right. How do we use it? Like, what's the purpose?
If we want, if this original function was the position of some particle being, I don't know, shot through space. I don't know what it would be. But if this was a position function, then I would use the first derivative to find the velocity of the particle. I would use the second derivative to find the acceleration of the particle.
All right.
Okay. Last problem from 3.3. Where is it? And which one was it? I know what it was. Y'all are going to do number 119 in the homework, and I'm not going to do it for you, but I do want to talk about 120 a second. Let me say one thing about 119. This is page 150. The velocity of an object in meters per second is v of t equals 36 minus t squared for values of t between 0 seconds and 6 seconds. So I'm not given the position function here. I'm given the velocity function. Just something to look forward to in chapter 5 when we learn to anti-differentiate, when we learn to go backwards. You give me the velocity function, I will anti-differentiate to find the position function. But we're not there yet. Find the velocity and the acceleration of the object when t equals 3. How will you find the velocity of the function when t equals 3? Just substitute it into the velocity function. That's what the velocity function gives you. But if you want the acceleration when t equals 3, what are you going to have to do? Find the second derivative and plug 3 into it.
Would you have to find the second derivative of that, or just?
Well, you know what? It would be the first derivative of the velocity function. You're absolutely right. I'm starting with the velocity function, so I only have to take the first derivative of it to get the acceleration function. If I had been given the position function, I would have had to have differentiated twice to get acceleration. All right. And then I'm just going to let you think about that question. Yes, sir?
Something interesting I just noticed is that if you plug in the 3 before taking the derivative and then don't do any work but just plug in the 3 alone, you'd still get the same thing.
I would be scared to do that on every problem.
Yeah.
Yeah, that may work on this problem. That's not going to work on every problem. All right. Last thing. This number 20 is just interesting. I like it. This graph has 3 functions. The position function, the velocity function, and the acceleration function. Now, none of them are labeled. Can you guess which one would be the position function?
The curve.
The double curve.
The roller coaster?
Yeah.
Yeah, but tell me how you knew.
Because it's a higher order.
It's a higher order than the other 2. Maybe this is a 3rd degree function that goes down on the left and up on the right. I know it's only odd degree functions that go down on one end and up on the other. So that one would be my position function. Which one would be the velocity function? The parabola. And which one would be the acceleration function? The straight line. What is the slope of that straight line?
Let's see.
Well, I don't actually mean for you to find it. I just meant it's a constant, right?
Yeah.
What does that say about acceleration?
Acceleration stays constant.
The acceleration stays constant. All right. Copy the graphs, blah, blah, blah. Identify each graph. We did that. Explain your reasoning. We did that. We don't need to go to mathgraphs.com and print a bigger picture because I have a zoom button on my Elmo. On your sketch, identify when the particle speeds up and when it slows down. Explain your reasoning. Now, I may have to make the graph pretty big for that. I may even have to, well, let me just think here. What about, you said this was the position function. So when the position function is increasing, what does that say? The position function doesn't tell you anything about speed. It's telling you the position of the particle. So the particle is going uphill to here, and then downhill to here, and then uphill again. Velocity can be up and down, or it could be left and right. If you're talking about left to right motion, then positive velocities to the right and negative velocities to the left. But you could look at the position function to tell when the particle is going uphill and when it's going downhill. What about the velocity function?
Oh, that would tell you speed with a direction.
Yes, don't get confused. Speed and velocity, they're not the same thing, and that's easy to get confused. Velocity may be positive or negative, but speed is always positive. Speed is the absolute value of the velocity. So, let me draw you a picture. If this is my velocity function, and speed is the absolute value of that, what is the speed function going to look like? Speed can never be negative. So this part that's below the x-axis is going to be flipped up above the x-axis.
Right.
If I had a highlighter, I'd highlight this is the speed function, because speed cannot be negative. So let me tell you what these 2 points are on the graph. If this is, if this is 1 1/3 and this is 4, I'm just trying to read that straight off the graph. And those are seconds. Your X's or your T's represent seconds here. When is the particle slowing down?
16 to, well, it'd be 0 to 1/3.
Yes, when the velocity is going downhill, not velocity, speed. Speed is decreasing from 0 to 1/3, and where else?
Did you say slowing down?
I'd have to tell you this too. That's 1, 2. It's hard to read that straight off the graph. It looks like it may be 2, 1, 2, 3, 4, 2. Yeah, I think it's 2 1/3. Doesn't really matter. I'm just trying to read those exact tick marks.
Yeah, it'd be 2/3 to 4.
It's decreasing from 2 1/3 to 4, and the speed is increasing where? 1 1/3 to 2 1/3, and then 4 to infinity. Oh yes, the graph does. That function was only good for times between 0 and 6. Yes. So you'd say it's increasing from 4 to 6. All right, I just wanted to show you the comparison of the graph of the velocity function and the speed function. Any time you have a velocity function, whatever is below the x-axis is going to be reflected over the x-axis, because velocity can be negative, but speed is never negative.